выходила из этого магазина, мы там поболтали что-то по математике, он так нас смотрел, велосипедист. Okay, so it seems time to start our morning session, and our first speaker is Denis Gaitsgory, and he will tell us about extension of Kazhdan-Lusztig equivalence with factorization algebras.
Yes, thank you. It's a great honor to be at this conference. So, Sasha Breverman said that it's only appropriate to talk to this conference to be really quantum, so we'll go quantum. Okay, so let me first remind you I can't calibrate my voice with this microphone. Is that okay? Should I speak louder or softer? Good? Okay. All right. So let me first remind you the usual Kazhdan-Lusztig equivalence. So we start with, let's say, semi-simple group G, or reductive. And so we consider the category that I call Kazhdan-Lusztig of G at level kappa. So this notation was introduced yesterday in Sasha's talk. So by definition, is this: we consider the affine Kac-Moody algebra at level kappa, and we consider modules for it, and we consider modules that are integrable with respect to G of O. So the arcs act integrably. And when I write a category, I always mean the derived category. So, and as we do in elementary school, I want the level to be negative, and I put negative sign, just emphasize word negative level. If something is positive, it will be a plus sign. Say again?
You make the minus sign smaller.
Even smaller? Yes. All right. So the Kazhdan-Lusztig equivalence says that this category is equivalent to what I'll denote rep QG. This is my notation for the category representations of Lustig's quantum group. All right. So sometime, and so the construction. So first of all, the nature of this equivalence is transcendental, because the dependence of Q in kappa, there's an exponential involved. So you really should think that this lives on the Betti side and this lives on the de Rham side, and you are kind of comparing apples and oranges. And the construction of this equivalence is not at all trivial. If you look at the papers, it's very substantial work. They construct a fiber functor, and
So it's apples and oranges because in this conference we don't allow analysis, only algebra and geometry.
well, you can take Riemann-Hilbert as a black box. So analysis done by others is okay. All right. So now, some time ago, I proposed an extension of this equivalence to the Iwahori level, and as I'll explain in this talk, this kind of thing turns out to be easier to prove, and hopefully you can recover from it the original Kazhdan-Lusztig equivalence. So what will be on the left-hand side? So I don't have as good a notation for the conference left-hand side, so I'll just denote it Iwahori. So I wish I had the symbols like Kazhdan-Lusztig, but I didn't invent anything. So that's my left-hand side now. And so what will be the right-hand side? It will be rep Q, and I'll call mixed. And I'll explain what that means. So as I said, here we're talking about representations of Lustig's quantum group. So you can think of its objects here. So let me write it like this. So these are vector spaces graded by the weight lattice. So lambda is my notation for the weight lattice. Lambda graded vector spaces. And so what you have an action of the positive part of the quantum group acts, and the negative part of the quantum group acts, and they satisfy relations among each other. So here it will be, the first two ingredients will be the same. acts, but the last ingredient is different. So instead of having Lustig's version, so here it's notation Lustig, so here. So this meant Lustig, L-U-S, but here we have a different guy acting. It's the De Concini-Katz version of the quantum group. So this is, if you wish, so the difference is only at roots of unity. So here you add the divided powers, and here you just have the original Chevalier generators with Serre relations. And you can, so a good way to think about these two algebras is that they actually are, so they're Hopf algebras in the category of representation of the quantum torus as Hopf algebras as in this category the duals of each other.
But do you mean that for irrational Q the right hand side is coincide?
They don't. So it's a very good question. So this acts locally finitely, and here it acts locally finitely. So in the irrational case, what you get is what you'll call quantum category O. So the positive parts act locally finitely, but not the negative part. So it's a really different category, and as it's supposed to be, because you don't want to get the same thing, because here you have Ibahori. So what we are trying to do in this talk, so I suggested to prove this equivalence to my graduate students, Charles Fu and Lin Chen.
So they are Hopf algebras in the category of Jeter-Drinfeld model.
I don't know what Jeter-Drinfeld is, but they are Hopf algebras in the category that will appear here prominently. I call it Rep-QT. It's representation of the quantum torus. As a monoidal category, it's just representations of the usual torus, but the braiding is determined by Q. So they're not Hopf algebras as is, but they're Hopf algebras in this braided monoidal category. So, so that's the project that they're working on to prove this. And so the purpose of this talk is that at the end of the day, the proof of this equivalence boils down to some computational problem, and I want to explain to you a device that allows to solve this computational problem.
But this equivalence is or is expected to be also transcendental, right?
In the same way as the original one, but what we'll do, we'll distill it to just Riemann-Hilbert. We'll compare both sides with something, and these two somethings will be just Riemann-Hilberts of each other. So it'll be. So before I proceed any further, I want to make a remark that it's kind of technical important for the way the proof goes. So namely, and it's a remark that Sasha made yesterday, that the original Kazhdan-Lusztig equivalence was formulated for the negative level. But in fact, you do have it also the positive level. The only thing is that it's an equivalence of derived categories which no longer respects the T structure. So the way it works is this, that if you take this category and the category at the reflected level, so I'll write kappa and minus kappa, but what I mean is that it's not strictly negative, there is a critical shift involved. So kind of the true zero is the critical. So there's a pairing between these two categories, namely you take two modules and you send them to kind of, it's called semi-infinite cohomology with respect to the Kac-Moody algebra. So the levels are such that the tensor product is exactly the level, which is exactly the minus the killing form, where semi-infinite cohomology makes sense. And this pairing is what's called perfect. So it identifies the category, the positive level, with what's known as the dual category in the sense of Lurie at the category of the level, negative level. So if you don't know what dual in the sense of Lurie means, it means, in practical terms, it means the following, that so these categories are what's called compactly generated, if you want to think about small objects, something like finitely generated. So let me say it like this, that compact objects in this category and compact objects in this category are opposites of each other. So if you wish, there's the formal duality procedure that goes from compact objects in one category to compact objects in the other category. And so to give you an example, if you start with a Weil module of weight lambda at kappa, under this duality, it goes to also the Weil module, but at weight kind of minus W, not lambda. So that's the way it works. Yeah?
Is this compatible with monoidal function?
in some sense, yes. Well, in laxly compatible. So, yeah, I mean, it's not a monoidal structure, it's a braided monoidal structure. Pavel, you had a question? No, you okay? So now the same thing happens for the quant group. So first of all, I want to put Q inverse, but if you think of what this category is, it's the same category as with the original Q, where you reverse the braiding. So I claim that there is also a pairing between these two categories, and that's defined as follows. When I identify the category with the reverse Q with the original one, this pairing goes to home from the trivial representation to the tensor product. And that also allows you to identify the category with Q inverse with the dual category. So therefore, if you have an equivalence like this, by formal reasons, you obtain also an equivalence between the categories at positive level. And let me just again emphasize that this category, unlike this one, does not respect the T structure. It's just all right. Pardon me? Rep QG. So I thought M2 started live here, but as a category, it's the same as just Rep QG. So I tensor them as representations of Rep QG and take home from the unit object.
They just have different braidings.
Different braidings. And whenever I write home, I mean R home. All my homes are derived. All right. So now, and exactly the same situation happens here. So instead of proving this, I'll be proving something which is technically more accessible, namely the corresponding thing at the positive level, if I only find the eraser.
It's under your nose.
Under my nose.
Your nose.
Notes. You have to work on your accent, Valeria.
Too late.
All right. So that's what we're going to prove. So now, what's the sensible way to do with this blackboard?
Slides left and right.
Yeah. Okay, let me leave this for now. We begin a new chapter. All right. So I'll now say a few words why this conjecture is more accessible than the previous one. And so namely, we'll have say a few words about the nature of this category mixed. So far, it might have looked as some kind of artificial construct, but in fact, it's not.
So I didn't understand. So this business between negative and positive level, did you extend it to?
I'm saying the same thing goes Ivahorian here.
Home from 1 to, you're not going to have home from 1 to a product to the Verma modules.
I can. All good.
Or 1 to 2.
Yep. It's not Verma modules. It's modules in the mixed category. And if you look at the usual category O, just finite dimensional, yeah. Consider usual category O. So the claim is that it's self-dual. And if you think what self-duality is, it's actually really home from the trivial representation to the product. That's the way the self-duality works. More generally, modules for the category of modules for the Lie algebra is self-dual. And the way this duality works, you take two modules and tensor them together, take home from the unit.
So if you have Verma module on one factor, you take dual Verma on the other?
It's not controgradient duality. It's what's called cohomological duality. It's not this.
No, but even if category O were semi-simple, for example, you take non-integer.
Let me say that under this duality, Verma modules go to Verma modules.
But how do you map one-dimensional space in a product of Verma module with a dual module?
Our home. So under this duality, Verma module with weight lambda goes to Verma module goes to something like this. So there is an R home there.
Is it our home to the algebra? You take our home to the algebra?
So the way the duality works is that you take M1, M2, and you pair them to home from the trivial to M1.
Okay. So this home will live in some positive cosmological.
Well, it's not controgradient duality, it's something else. All right. All right. So I want to explain a little bit about the nature of this category. Namely, it's the following one. So, as I mentioned, you can consider UQ and plus it's a Hopf algebra in the braided monoidal category RepQT. And you can consider the category of its left modules, and let me say nilp, so I ask the action to be local nilpotent within this category. This is, because it was Hopf algebra, this is a monoidal category, but it has an additional structure, so it's monoidal, but you can take its objects and tensor them on the right with objects from RepQT. So what we call it acquires, it's a monoidal category equipped with an action of the braided monoidal category RepQT. So there's a notion of an action of a braided monoidal category and a monoidal category. And in these circumstances, you can take what's called the relative Drinfeld center. So usually if you have just a monoidal category, you can take its Drinfeld double. But you have a monoidal category equipped with another action of a braided monoidal category, you can take what's called the relative Drinfeld double.
So action means it's a map into the Drinfeld center?
It means exactly that. And let me say, in this case, it's right action. So these things matter.
Which means map to Drinfeld center that opposes the braid.
Correct. And in this case, you can take the relative Drinfeld center to this action. So if you wish, you're now looking at a universal braided monoidal category that acts on the left on this one in a way that commutes with the right action of this. And the
So this is the same as to consider categories, there are categories which are enriched over this braided.
I'll get confused about this because I don't like the word enriched, but I don't know the word enriched, but something like this. There aren't two ways about it. It's kind of pretty straightforward definition.
It's another way.
So, long story short, is that you can take this relative Drinfeld center, and what you get is exactly RepQ mixed. And G. And this is just the reflection of the fact that I mentioned that this guy is the Hopf dual of this guy. So that's all it says. So this is one transformation that I'll perform. And another transformation that I'll perform is, so I want to reinterpret this category itself a little bit. So I want to, look at modules equipped with a local nilpotent action of some algebra, and what I want to do, I want to apply causal duality. So this category itself, so let me just, this category is modules with respect to the causal dual also within RepQT. And what this causal dual is it's R home, well, I read home, from augmentation to itself over UQ and plus Lustig. So it's always Lustig here. So you take this interesting algebra of self-acts of augmentation over Lustigs, and So you consider modules over it. Now, because this was a Hopf algebra, what you end up here, it's not just merely an associative algebra, it's what's called an Ito algebra. So if you have a braided monoidal category, such as rep Qt, it makes sense to talk about Ito modules. It makes sense to talk about Ito algebras and yeah, don't confuse dk and kd. Kd means Koszul duality, and dk means the Concini cuts.
After all, it's a conference about quantum structure, so things don't come in.
See, the Concini cuts, Koszul duality are 4 different guys.
I only met 3.
Yes. All right, so just continues with this topic. So what we have said, rep Q mixed is a relative Drinfeld center with respect to rep Qt for the category of modules, left modules for home k to k, uq Lustig and plus. And now there is a, and where I repeat that we know that this algebra is not a mere algebra. It's an Ito algebra which gives the category of modules for it a monoidal structure. And now there is a general theorem that
Sorry, which one is an Ito algebra?
this, yeah, this X, if you start with associative algebra, the X algebra will be just an associative algebra. But if you start with the Hopf algebra, the X algebra will have an additional multiplication, that's the Ito algebra. And it's an Ito algebra in the category, so you can talk about Ito algebras within braided monoidal categories. It's an Ito algebra within this braided monoidal category. And we're kind of taking everything relative to this. And now there is a general observation that due to Lurie, that in this case, if you take the center, what you get, you'll get the category not of modules, but what's called E2 modules. So again, within rep Qt. So we've interpreted this mixed category, again, as follows. We take this category representation of quantum torus. There exists a certain Ito algebra in it, and we're taking the category of Ito modules for it. So I now perform one more manipulation to bring it to geometry. Pavel, are you okay? You look unhappy, so I want to...
So you wrote that the rep Q mixed of T was some Drinfeld center, relative Drinfeld center, and now you're...
I'm further manipulating this.
I don't, but is it the same?
Same. I rewrote here. I rewrote what this category was. This category was the category of modules for an Ito algebra, left modules. And the Ito algebra structure gives this category of left modules a monoidal structure. And I'm saying in this case, if you have an Ito algebra, if you take the category of left modules, if you take its Drinfeld center, what you end up with is the category of E2 modules for this Ito algebra. And that's what's written.
Okay. Can I just,
Yeah.
from a super pedestrian point of view, it seems like this relative Drinfeld center means you have something with an action and a coaction of your two ends, and then you use Koszul duality to turn the coaction into another action, and so now you have two actions. I mean,
It's exactly that. It's exactly that.
So you're using the fact that the full dual to Hopf algebras is equal algebras, yes?
Exactly.
So instead of algebra with multiplication and co-multiplication, we have
Yes. Yes.
Okay, now
Yeah? All right. So the next step will be to further manipulate it to get to geometry. Exactly. So if you just have a, let's say, augmented associative algebra, call it A, I'm saying that A mod nilp is the same as Koszul dual A mod. Okay? So that's exactly what's being used.
but if A is a half-algebra, I will do it like this.
Yes. So the next step will be to further rewrite it in geometric terms. So here, well, to explain it properly takes a long time, so I'll have to just make certain leaps. So let me say it like this. So we consider a configuration space, and I can call it of some algebraic curve, x. So you can also think of it x to the power lambda neg. So let me explain what it means. So this is the moduli space of expressions just formal sums where formal finite sums where xi's are distinct points of the curve, lambda I are elements of lambda, but I don't allow arbitrary elements. I allow elements that belong to where lambda neg is the positive integer span of negative simple roots. So just combinations of negative simple roots with positive coefficients. And so, and if you think what it is, it's just a disjoint union numbered by the total degree of partially symmetrized power of the curve. Basically, just along each simple root, you have a symmetric power of the curve. So this is the configuration space, and there will be one more version. So let's mark a point on the curve, call it x, and I'll have another version. I call it infinity x. So it's the same kind of thing. Let me call it maybe x0. Lambda I xi plus lambda 0 x0, where these guys are as before, but the difference is that now this particular lambda can be an arbitrary element of lambda. So if you wish, I can allow arbitrary poles at my distinguished point, and everywhere else I require positive behavior. So this thing, as I said, is a disjoint union of partially symmetrized powers of the curve, and this is an in scheme. So the way it looks is that if you have, so if you consider, you can take inductive limit of nth symmetric powers of the curve, where the maps are given by adding the point x. So it's an in scheme that looks like this. Vitya, you okay? All right.
Where is this Z dol? Is it dol at the red?
No, where?
On the top, the Z
Drinfeld.
Drinfeld.
Sorry.
Can you comment on the expression in next line? From K to K.
Home to K to K.
Line below.
Below.
The left-hand side.
There is a
form, but there is no
You said modules in which category, but you didn't say over which algebra.
Yes. Okay.
Yes. Sorry. All right. So far I introduced geometric space. So again, my goal is I want to rewrite this category in geometric terms, and this is what I'm in the process of doing. And basically what I'm doing, I'm rewriting the contents of the book of Bezrukovnik and Firkenberg and Schachmann. I'm doing it digest in 5 minutes of what takes 300 pages. So therefore, don't be surprised that I'm skipping a lot of details. So over this configuration space, there exists canonically defined line bundle L. So let me say what its fibers are. So the fiber of L at a configuration that looks like this, it's a tensor product over I. So what you do, well, it's supposed to be a line, so I'll tell you which line it is. You take the cotangent line at this point and you raise it to the following tensor power. So let QZ be the minimal integer valued quadratic form on my root lattice. So I evaluate it at lambda I, and let B be the associated symmetric bilinear form, so the minimal one. Let's just for simplicity assume that my group is, doesn't matter, minimal form, and lambda I against rho. So this is an integer, and I'm raising the cotangent line to this integer power. So now it's not a difficult thing to see that it's indeed glues to well-defined line bundle. So, and moreover, so maybe I should have said like this, that so this configuration space breaks up into connected components given by total degree, where each conf lambda looks as follows. So if I write lambda as a sum of negative simple roots with non-negative coefficients, then this is just the product over vertices of the Dynkin diagram of partially symmetrized powers of the curve. And so inside here, there's an open subspace where I take simple divisors. And just if you think that if you take lambda to be a negative simple root, this integer vanishes. So what you see that this line bundle is canonically trivialized on this open locus. Is over conf 0. Its locus were of simple divisors. It's kind of an important observation. So, all right. Now, okay, sorry. Now it'll be bad usage of board space. So now remember, I had a quantum parameter Q. So now let's recall the following. If you have a space and a line bundle and a invertible complex number Q, you can consider, instead of just sheaves on the space, you can consider twisted sheaves. So you can consider sheaves on the total space of this line bundle with punctured zero section, which are monodromic along the fiber, with monodromic given exactly by Q. So the category that we'll consider is, I'll call it sheaves Q on conf. So what I mean is I'm using this number Q that appears as a parameter in the quantum group and this particular line bundle to construct this twisted sheaves. And the same story, you can do configurations with this marked point. QZ, if you wish. So if you wish, so I have an integer value quadratic form.
No, I understand, but somehow it should not be confused with Q, with number Q.
But that's why it's QZ. Yeah. All right. So again, please apologize for bad boardwalk work. I'll be.
But I don't understand. So you said originally the Q was like Q is supposed to be exponential of cup, and it's 1 over cup, and it is not a number. It's some kind of quadratic form. Yes. So now you're saying that Q is a number.
Okay. Let's assume that our root system is simple. So in this case, let's talk about Q. Forget kappa for a second. So this Q, okay, this is basically Sasha's question. So the true Q is a quadratic form on the root lattice with values in C star. That's the true Q.
Yeah.
But any such Q can be written as follows. It's a complex number, Q, to the power QZ. So when most people write quantum groups, they use complex number as a parameter. which translates to the quadratic form by this formula. And in this talk, I adopted this convention.
Okay. So that's why this notation is not good.
Yeah. I was hesitating which notation to use, and I just.
Could you call it kappa Z?
No, kappa has values in not C star but C, and they're related by the,
The kappa.
they're related by the exponential. So I really don't want to confuse kappa and Q.
No, of course.
Yeah.
Maybe it should be called C because it's Cartan matrix. It comes from Cartan matrix, right?
Let's stick with it first. I think it's.
This is lambda actually you get negative weights.
Yes. Yeah, my weights.
And that includes 0.
Pardon me?
But that includes 0.
I exclude 0. I write like neg. Neg might I throw away 0.
And what's this BZ?
So QZ was the minimal quadratic form, and BZ the associated symmetric bilinear form.
Okay.
So now I'll state another version of, well, another theorem of Lurie, rather a version of it, and it says the following, that okay, so construction Lurie, that let A be an augmented E2 algebra in rep Qt. Then to this A you can attach what I call omega A, and see there is a Q here, and it's a sheaf which is twisted sheaf by this particular Q on the configuration space, which is not just a sheaf, it's what's called, it has a structure of factorization algebra. So let me say it, it's factorization algebra here. So factorization means the following, that so you have the addition map on divisors, and inside here there's an open locus where these pairs of these divisors have disjoint supports. So let's call this map add. So factorization means the following, that if you pull back your omega A by means of this addition map, it's supposed to split as an external product of omega A by itself, but not over the entire thing, but over the disjoint locus. And so
So you start with an equal algebra in rep Qt.
yes,
And out of
that I produce a factorization algebra in the category of this twisted sheaves. The twisting is exactly the same Q.
It seems like left-hand side depends on down torus and right-hand side depends on Northeastern.
No, rating
Rating
depends
depends
on
on-
B depends on
Negatively graded. Very good question. So it doesn't depend on the root system. So it depends on the semi-group there. So far the root system hasn't entered. It's just it's a game just about the quantum torus.
No, but the quantum torus has the braid.
It's a quantum torus. Well, it could be just any torus with the braiding. So torus is a lattice. The braiding is given by quadratic form values that start on this lattice. This lattice didn't have to come from the root system. All you need is the lattice and the quadratic form.
but don't think this lattice can be somehow related to an integral lattice, because when you define
Pardon me?
can you define twisting for any quadratic form?
Yes. Absolutely. All right.
This is the sheaf or a complex sheaf?
Very good question. So when I talk about E2 algebras, they are arbitrarily derived, so a priori it will be a complex of sheaves. However, so if my E2 algebra is perverse, I'll say what it means in a second. So E2 algebra is perverse if and only if this guy is perverse. So I have to tell you what I mean by E2 algebra being perverse. So remember, E2 algebras, this category is equivalent to the category of Hopf algebras by causality that Pavel asked about. Yeah, so you apply this procedure. E2 algebra is perverse if and only if, when you turn it to Hopf algebra, it sits in 1 degree. So if you start with a classical Hopf algebra, turn it into E2 algebra, and do this omega, it becomes a perverse sheaf. And this is our case because our UQN plus Lustig was a classical Hopf algebra. It was in degree 0.
So in particular, this isomorphism, it's really isomorphism.
Pardon me?
This isomorphism you're on, it really is it, the one, that one.
Yeah?
That's really an isomorphism. There's no
Yeah.
quite isomorphism.
It's really an isomorphism, so we are really dealing with objects in the abelian category, and it's very important for what will follow next. Pavel, are you okay? Yeah? You look like you want to ask a question.
No, so we are considering a simple group, right?
Let's for simplicity, yeah. Or you can do it this game along each simple factor. So there is this construction, and so now I come to the punchline. It's it's addition of divisors.
And the stocks are some torques, right?
Pardon me?
The stock of this guy is some torque.
Yeah, I should have said the construction is such that I am already in E2 algebra. The stocks are that A. The Schwick stocks are given by specifically A, just products of copies of A, each in the corresponding degree, and the structure, the sheaf structure, basically how you do specialization, is exactly determined by the E2 algebra structure.
The contours, if you start with the whole algebra.
X, yeah. Yeah. But we don't want to unravel the causality. Just in this case, just the stocks, the Schwick stocks are what they are, and the E2 algebra structure tells you how to fuse them. All right. So now I'll state second part of Lurie's construction. So there is a theorem, again it's Lurie, that says that in this case, if you consider the category of E2 modules for A, it will be equivalent to the category of what's called factorization modules on inside sheaves on this configuration space with a mark point. So I should have said that for both of these theorems, so here we need to take X to be A1. So let me just repeat what I said. So I said that starting from A, we obtain factorization algebra on the configuration space itself. But now, given a factorization algebra in the configuration space, it makes sense to talk about factorization modules on the configuration space with a marked point. So what I mean is this, that in addition to the original addition map, there is also this addition map. And so a factorization module is, so it's again, it's a sheaf here equipped with an identification with omega A box times F, but again, not over the entire thing, but where you restrict to the disjoint locus.
And if X is more general, then A should be replaced by the factorization homology of omega A?
No, if you want to do on what's called curved X, you need a ribbon structure. You need automorphisms of the circle to act on the whole thing.
Well, rep Q of T is really big.
Yes, but rep Q of T is ribbon, but you also need A to be compatible with ribbon structure. It's a condition on A.
And this one is
this one is satisfied.
But then what I'm saying is correct?
Say it one more time.
That we should replace A by factorization homology of omega A.
No, just as is. I'm saying that you
I
can.
don't understand, but left-hand side doesn't depend on x.
Correct. And this the ribbon structure, so what you look at this category, if you look at the definition, the only thing that matters is a formal neighborhood of the point x. And the ribbon structure tells you that if you choose a coordinate, it will canonically be independent.
Oh, it doesn't depend on x?
Yeah, this category it only sees the neighborhood of x.
Ah, x0. You called it previously.
Sorry.
Ah, okay. Because it's the conf infinity.
Yeah.
If you took conf the previous version, then
So see, you can, well, it's a philosophical debate if you think of omega as depending on x or not, but once you fix the factorization algebra, if you look about factorization modules, again, they only depend on the formal what happens near this particular point. All right. So I'm 1/3 through my talk. Okay. Summary. So. Summary is that rep Q mixed G can be identified with the category of, let me call it omega Q Lustig factorization modules in the category of twisted sheaves on this configuration space, where omega Q Lustig is this omega attached to the algebra, which was the Koszul dual of UQN plus. By Lurie's construction. So that's the summary of this talk. So basically what we have done, we've translated the left-hand side into geometry. So it's factorization modules for a certain factorization algebra. And again, this is what distinguishes this mixed category from the original one. It would have been impossible for just a rep QG. So here we're using it in an essential way. The mixed was really using all of this stuff. So that's why this particular version is more amenable to geometric treatment. So what I'm going to do now, I'm going to pass through the Kac-Moody side and do the same thing. So let me just maybe just do the summary of what I'm going to do now. So I'll perform an analogous procedure on the Kac-Moody side, and then I'll compare the geometric parts. So that's the plan. So how are we going to do this? So our starting point is the functor of semi-infinite cohomology with respect to loops into n. So let me denote it.
How are we going to do what we can?
Say again?
How are we going to do that? I mean, how are we going to do what?
So I'm going to perform a similar procedure on the Kac-Moody side and compare the geometric sides. So now,
The functor from some
yeah,
representations to some
factorization modules. So this is the functor of, call it with respect to loops into n. So it's a functor from, well, you can consider modules for the Kac-Moody algebra. Well, you can do it at any level. All they need is integrability with respect to T of O into the Kazhdan-Lusztig category for the torus. And so it's a functor of, again, as I said, semi-infinite cohomology with respect to loops into n. But if you think of what it does, it has an enhanced version. So it can be enhanced to a functor that I'll call enhanced and it will go for what's called factorization modules. So inside this category, there's also a factorization algebra, which is obtained by applying this functor to the vacuum module. And so if you think of what Kazhdan-Lusztig category for the torus is, so it's a semi-simple category with a non-trivial braiding. And so you can equate this category with, call it, on the same so you can think of this category as also set of sheaves that should D modules. Yes. So I'm saying that you can think of objects of the Kazhdan-Lusztig category for the torus also spread over the curve as not sheaves but D modules on the same configuration space and twisted in the same way. So we had a line bundle, but now, so if you're working in the Betti context, you need an invertible complex number to obtain twisted sheaves. You're working with D modules. What you need is a complex number, not invertible.
Just read what's written. So it's omega sub k. First of all, what is omega sub k?
Yeah, so kappa.
And then
So
mod and then
factorization, but within D modules on the configuration space, where omega kappa is the factorization D module that corresponds, well, to this factorization algebra in the Kac-Moody setting. So you obtain this functor.
So the idea is that you had, in the quantum group case, you took a homology of nilpotent part and said that Kazhu dual to E2 modules of this thing. And now you are doing the same thing, but you take a homology of affine nilpotent.
Yes. Yeah.
Part, and again, this will be some kind of E2.
It's, well, we're now in the Durham context, so we're talking about kind of factorization modules for factorization algebras.
Right.
However, whereas on the quantum group side, the fact that RepQ mixed was equivalent to factorization modules was basic combination of Lurie's what was the result of Lurie's theory. On the Kac-Moody side, it's not at all guaranteed. We have a functor in one direction. You just take the same homology and you get the category of modules for this factorization algebra. And you don't know if it's an equivalence. If it started, well, it's certainly not an equivalence of this entire category. It would not be an equivalence if I start with the Kazhdan-Lusztig category, but I do claim that it happens to be an equivalence if I start specifically with Iwahori integral representations. So you need to use something very specific there. So now let me state the two main theorems that make all this stuff work, and then I'll pass to the kind of the computational core.
You're not going to have D modules, regular holonomic D modules?
They are regular holonomic D modules.
So you will not have any objects here which are not regular holonomic?
No, they're all regular holonomic. We are.
well, I mean, you will be regular holonomic. You start with the Iwahori integral. You start with arbitrary Iwahori integral.
No. If these arbitrary guys are at a point, they're still regular holonomic. In regular holonomic, but.
So that means that if there is no objects there which are not regular holonomic.
Correct.
In this thing.
Correct. And now, so this conjectural equivalence of the Kazhdan-Lusztig equivalence amounts to the two theorems. Theorem 1 says that under Riemann-Hilbert, what I called omega Lustig Q, which was a factorization algebra on this configuration space, corresponds to what I'll call kappa, which is a factorization D module on the configuration space. And this is for kappa positive. So this is kind of really important because this assertion would completely fail at the negative level, and you'll get something interesting, but not that. So it basically says that the factorization algebras that I got into sides are the same. And theorem 2 says that this functor, what I call semi-cohomology enhanced, which no longer mentions the quantum group, so it's a functor that I now regard specifically the Gaitsgory category. It goes to omega kappa modules factorization on the twisted D modules on configuration space with the marked point is an equivalence. So once you prove these theorems, you are in business. And so I want to spend the remaining 3 minutes to, well, basically explain what these theorems amount to. So it's not...
So you're saying that Kazhdan-Lusztig equivalence, the usual Kazhdan-Lusztig equivalence, falls only at negative level. And you're saying that if you go to Kazul tools, then it has to fall only at positive?
No. So that's what my remark, kind of 10 minutes to the talk. I'll prove this at the positive level, and I deduce the original one by applying this duality. Remember I talked about duality? The reason I mentioned it...
Yeah, but this is false or negative, or what? Theorem 1.
Theorem 1 is false for negative kappa, and this theorem is false for negative kappa. This theorem is at the positive level.
So this Kazul duality somehow switches negative and positive.
Where is Kazul duality?
Well, I mean, this is like this E2 or E2.
So E2 was for quantum groups. It doesn't know the sign.
Okay.
It's the sign. The sign is only felt for Kac-Moody.
Yes.
So these two theorems are only true at the positive level, but as a result, I do obtain the equivalence between this and the rep-Q mixed for the positive level.
Yeah.
And then I apply duality, this homological duality that I talked about, and to deduce the original one for the negative level.
Yeah. So duality exchanges the sign. Changes.
Correct.
The sign.
But it's not Kazul duality. It's this.
The okay.
Yeah.
That's very good. Okay.
So all the categories that you're writing right now is the right category.
Yes.
So
Yeah.
it's only influenced with right.
Yes.
There is no abelian statement for
Positive level. There are no abelian statement for the positive level.
and no abelian statement for integral, for Gaitsgory integral. Yeah. Or
Correct. Yeah. So okay. So I want to just say what these theorems amount to, and they amount to something interesting. So here I'm stating that under Riemann-Hilbert something goes to something, but well, I'm sorry, I may take another 2 minutes because I mean that's kind of the punchline of this talk. So there's a computation here that's interesting. So I want to characterize this omega Q Lustig. So it's a factorization algebra. It's a factorization algebra. So I want to say what it looks like. So, well, it lives over conf, and conf is this joint union of these guys, and inside each of these guys there's an open part. So on the open part, this omega Q Lustig is a sign local system. So remember, I'm talking about twisted sheaves, but my twisting was trivial on this open part, so therefore it's the same as usual sheaf, and well, it's basically the only irreducible factorizable thing that exists, and because of the sign rules, it has to be the sign local system. It's one-dimensional there. And the question is how you extend it across the diagonals. And so because of factorization property, you can proceed inductively, and here's the procedure that tells you what omega-Lusztig looks like. So let's fix my point x0, and let's denote by I lambda the embedding of the divisor lambda times x0 into the configuration space. So the theorem is that omega-Lusztig is characterized uniquely by the following procedure. Wing procedure. So let lambda be in lambda neg, and lambda is not one of the negative simple roots. So what you have is the following. If you take the star fiber of your omega-Lusztig there, it lives in degrees less than or equal, strictly less than -1. And if you take the Schrieg fiber, it lives in degrees, homological degrees greater than or equal than 1. So, and it's kind of, the fact that it's a strict versus non-strict inequality is very, very important. So if you had non-strict inequalities on both sides, it will only say that this thing is perverse. And so what this says is that, so let me denote by J this open embedding. So this line translates to the fact that if you take the Schrieg extension from its restriction to the open part, then this map is a surjection. So it's not only a perverse sheaf, it's actually a perverse sheaf, but it kind of is surjected upon by if you swapped this non-strict inequality to here, it would be the dual thing. It would say that this embeds into the star extension of its restriction to the open part. And what you will get, you will get not the Lusztig version, but the Concini-Katz version. So the Concini-Katz and Lusztig are exchanged by their duality. So therefore, if you want to prove theorem 1, you're looking at this omega that's gotten by the procedure of semi-infinite cohomology, and you want to prove these two estimates. So it's estimate on the Schrieg fibers and the estimate on the star fibers. So you know how to do Schrieg fibers, because Schrieg fibers are given by semi-infinite cohomology. If you can calculate semi-infinite cohomology, and then you will be able to prove this, and it's an easy thing to do. So the mystery of the game is how do you calculate star fibers? It's non-trivial because you apply this factorizable procedure, you get this factorizable sheaf. Again, you kind of a priori know the Schrieg fibers, but then you have to somehow calculate the star fibers. It's not clear how to do. And that was what prevented, well, that was the obstruction to proving such things for a long time, because we didn't know how to calculate star fibers. And theorem 2 is something very similar. So you have to, at some point, you have to calculate the star fiber. So now I'll quote the kind of the key calculation.
Theorem 2 is something, statement something is something. I mean, theorem 1 is a statement that two sheaves are isomorphic, and theorem 2 is a statement that two categories are equal.
So
it's not.
Yeah. So for theorem 2, you'll have to show that some standard objects go to standard, and then you have to show that if you apply this functor to the standard object, you want to show that the star fiber equal to 0.
But if you check that, but you also have to check something on Holmes, right?
It's kind of, well, it's kind of automatic. It's what I said is equivalent to the fact that standards go to standards, costandards go to costandards. So there is a key calculation thing. It says the following: that if you take, you say it like this, if you take lambda star of this cohomology enhanced of some representation. So the question is, how do you how can you possibly calculate it? So the theorem, which is new, says that you can actually calculate it as follows. The dual space of this is isomorphic to the following. You take and this is at the positive level. You will take semi-infinite cohomology, the negative level of minus lambda, where this duality is the duality that I mentioned 15 minutes of the talk. This is D is duality functor between compact objects at the positive level to compact objects at the negative level. So again, let me just emphasize, you want to calculate the star fiber of something that you got by factorization. You do know how to do it, but the claim is that what you can do, you can apply the duality functor and take the semi-infinite cohomology negative level and just dualize. And it's a non-trivial theorem. To prove it, you use global geometry, use Bun-G, use geometric Eisenstein series. You can use a lot of stuff, but at the end you can prove it.
But is there an easy way to see a map in one direction?
No, not at all. I mean, there isn't an easy way to see this. Well, the star fiber is kind of mysterious. But you don't even, so to prove such things, you don't even have to have a canonical isomorphism. You need to have some isomorphism.
Are there questions or comments?
So you said that somehow you consider the dual thing, vertical thing, then instead of Lusztig version, get the consumer version of this positive part, and is it relevant for some kind of other, I mean, for some equivalence to categories? Just use this whole stuff to actually prove that somehow some kind of category all parts.
Can you say that one more time, the first part of the sentence?
You made the remark that
Yeah.
if you consider the Ferrier dual of the omega, then you get a similar thing, but for the constant continuum.
Yeah, it is relevant. So a claim is that in theorem 1, if you do it at the negative level, you will specifically get the continuum version.
Okay, but somehow can you use that remark to prove some? Does it give rise to some kind of other equivalence of categories or not?
No, not to my knowledge.
Quantum?
Not to my knowledge. But this observation is used as a computational tool.
But could you maybe use it just to detect the negative level directly without?
No, because you don't want to see factorization modules for the continuous Katz version. It's kind of wrong category to see. So yeah, I have thought about it, but so the answer that I don't know how usefulness of this fact.
And does this theorem lead to any? So Kazhdan-Lusztig paper was written in order to calculate characters of quantum groups of roots of unity, and eventually
Yes.
groups of characteristic field.
Yes. So
can you do something similar?
yes. So unfortunately, Edik is not here, so I don't know whether, for example, semi-infinite cohomology of the vacuum representation at the positive level was known. Misha, do you know? But this computation tells you, and that I wouldn't know any other way to do it, that, for example, if you want to calculate semi-infinite cohomology, it actually equals the cohomology of Lustig's UQN plus. It's a non-trivial fact. So again, I'm not calculating something like characters,
No, I mean,
but
you
it
can
has.
calculate characters for this kind of mixed. If you consider this quantum group, mixed version of quantum group at the root of unity, and consider this category O, and if you care about characters of simple modules there,
Yeah, you can do this.
This in principle gives you an answer.
Yeah. So yes. Yeah. So yeah, the original equivalence that I said, in the same way as the original Kazhdan-Lusztig tells you about characters of Iwahori representations, not GFO representations, for example.
So what happens if the algebra cannot be factorized? Can you obtain an extension?
I don't know. I mean, these algebras are factorizable kind of by construction.
What is some of the room at 11:05, and I believe there's a coffee now.
T is in 321, so on the third floor, like yesterday.